So welcome everyone. The third session of Noise Lab, good old Noise Lab. I'm screenshotting you for attendance. And I've catched the question from Marin just before I had to restart the whole thing. And it happens to my camera blocks after I use it and then stop using it. It tends to block out. So last week what we've done was essentially percussion synthesis. Started with a kick, got down to a snare, and then did kind of a hi-hat type of sound. In fact, I probably still have the graffle. Actually, what we've done last week was pretty much straight, middle of the road kind of thing, because we wanted to make sure that open recent, no? We wanted to make sure that the things are quite straightforward. And what I've done as well is I've started making graffles. That's just not one of them. It seems like I've removed it, but actually this is another audio synthesis graphole. So the idea was that on a flow chart, we can observe the signal flow slightly better. And therefore, I have supplied flow charts and asked you to create patches from that, just to kind of get you going. There is no replacing your own patching around. So I guess, how is everyone in this group? Are we all quite comfortable with the basics of synthesis, with the kind of basic patching in VCV? You're welcome to talk into the mic. You can also post into the chat, whatever you prefer, just to see where we are.
I'm pretty comfortable with patching in VCV rack. It seems quite similar to most other synths that I've used before. So, yeah.
Excellent. Okay, pretty comfortable. Okay. Well, it looks like, I mean, it's kind of evident that we get a good amount of interest at this stage. So we have just another week next week. So yeah, after the first week where we just scratched the surface just to get into it and just got straight to funny feedback loop to create chaotic stuff, which was successful in my opinion. In the second week, as I said, we've done percussion synthesis. So essentially just sticking envelopes into different parameters and getting friendly with things. In fact, the bit last week, I'm actually unsure how, maybe probably some of you have followed last week. The interesting thing was that I did a bit of calculation in terms of, you know, suddenly we had this patch with the FM side and the noise side, both kind of under envelopes mixed together, essentially straightforward. And then I did a quick calculation how many combinations we have if we take every dial range and split it up in 5 discrete points. And the calculation gave us something, I don't know, 10 to the power of something combinations. So which was a kind of a warning sign for myself and others who tend to you know, go for the tech. I mean, we are music techs, right, in a way. So if we were pure musicians, we'd probably be busking rather than, you know, trying to uncover new modes of new tech, really. So yeah, it's an exciting thing to be on the frontier, at least your own frontier, right? Everyone's just on their own frontier, I guess, in a way. But the message there was, don't forget that just a simple patch with 10 parameters has the amount of combinations that you can't really get to. No chance you can get to it. And the pitfall there is that you take one dial, you go up and down. It's like, okay, that does that. The other one, okay, that does something else. Okay, that does something else. But actually, what one dial does might largely depend on the settings of all the other dials. So if the patch is somewhat interesting and potentially non-linear, then you can play with the dial, but then reset all the others to a different state, and then play with the same dial to discover that it suddenly does different things or somewhat unexpected things, which will be the property of the nonlinear stuff. Nonlinear meaning that the parts don't add up to the sum. So I've taken the chance and talked a bit about this chaotic stuff as well. So it's all nice and exciting, in my view, and yeah, VCV Rec seems to be a growing community, which is great. And it has a lot of different things. So what I've promised for today and what I had in mind was essentially getting to some core modular principles, processing principles, that are not very often present in other synthesis software and the likes. And this has to do with the fact that analog computing is what got us to the moon, right? So in the 60s, we didn't have digital computing. We only had analog computing. So you've seen me talk about multiplication and addition. That's actually arithmetic of it. That's that. So the model that calculated the landing on the moon, to the extent you're not a conspiracy theorist, or that's even a label, to the extent you believe that that was a real event. It seems like it was. I wasn't there. But the landing on the moon was computed with an analog computer. So what you actually do in that situation is you create a model of all the physical properties, right? Because as you have physical equations, you know that certain things equal something times something else minus something else over something else. And that model is actually a live computing situation, and you throw in the, I don't know, the weight of the 3 astronauts, and on the output of the analog computer, which is patched just like our audio patches are patched together, you get, the amount of coal, whatever, the heat, the whole calculation, the whole computation is actually an analog circuit. So that's the heyday of analog computing. So because that is the background that we work against, which is a total mind blow, to avoid the F word, therefore we have analog components which are not just, they're just not meant to be used for synthesis, but they are there. These circuits are there. So that's why it's quite an exciting domain to explore. And obviously, it gives you a whole different insight on signal processing. So if you have some experience with a digital counterpart, it can be quite exciting. So one of the things which is really exciting, but I won't go into it much, is that in physics, what we have are processes called differentiation and integration. And I have no clue if you guys heard of this in some BTEC levels ZSPQ34. But just as a matter of, opening up the perspective and really getting to understand the wider picture, these are crucial relationships between certain physical magnitudes. So, for example, speed is actually distance over time, right? And time can be conceived of as a separate dimension there, right? And actually what you have is that the speed has everything to do with the gradient of position. So if you plot your position graph, like, okay, I have my position over time, right? Then the steepness of that graph is your speed, right? So how fast, how much displacement you have over a unit of time, that's your speed. So that is the gradient, that is the differential of position, speed. And then acceleration is the differential of speed. So how much change in speed you have per time unit. And then you can go the other direction as well. You can integrate. So if you integrate acceleration, you get speed. And if you integrate speed, you get position. So that's the math, that's the physics there. And actually with differentiation, you're looking at the steepness of the graph, which is the gradient. And with integration, you are looking at the surface beneath the graph, which is the surface. And the surface, the integration is also the process that takes us from signal to its energy. Okay, so you might have heard me say that the energy of a signal is the surface between the signal and the zero axis. So you understand that the longer the positive value, right, the more energy. Whereas this value is fixed. If it stays positive, the energy is actually growing because the surface beneath the graph grows. Okay, so that's exciting and fun, and you know, if you have any inclination to get a dopamine rush from numbers and physical descriptions, this should do a good dose. Especially if you get the time to properly explore it. I'm just putting it out there in kind of in some broad terms. And the funny thing is that an integrator is a low-pass filter and a differentiator is a high-pass filter. And that's when can't compute, the dots start to do funny things. How on earth? Why on earth? Well, in any case, you know, we had to take the man to the moon with analog computing, and we had to integrate and differentiate. And these two domains meet right there, because a high-pass filter is taking the differential of the signal. So I'm not sure if you guys had this perspective on it, because I'm not doing APDI. I think you haven't seen me in the APDI lecturing role. So if you subtract a sample from the current sample, the previous from the current sample, just that, subtract one value, amplitude value minus the other, what you get is a high-pass filtered signal. And if you add the two samples, you get a low-pass filtered signal. Now, adding two samples is a kind of averaging filter, as we call it, which is not equal to integration, but it's a similar thing in the sense that both are low-pass filters. So the engineering, the amount of stuff behind all of this is just huge and as exciting, in my opinion. So unless there is any questions into the philosophical stuff here, yeah, and 4K of the RAM, except that we didn't get to the moon with 4K of RAM because with analog computing you don't have kilobytes like that, right? Bytes and bits have everything to do with the digital description of signals. And in analog computing you have the number of modules, the number of patches, and they just run continuously, right? So that's all fun and great. Now back to having more fun with making these moon landing ideas into our slaves, into our noise slaves. Let's see what we have going. So the first thing I want to introduce is a matrix mixer. Okay, so this will be my main tool for doing anything from now on, because it is just fine. Okay, because it is just amazing tool for doing real stuff, and allows you to feedback very quickly. And if you know me by now, you will forget everything you ever knew. I'm all into inducing interesting feedback in our computing, in our patches, because it will produce somewhat unexpected, chaotic, interesting, unaccounted for sounds. Okay, so this is my matrix mixer. So what you see here, it's a count module. So if you want to get access to this, what you have to go is go to library. First of all, if you're never logged in, if you haven't created a username, you have to go through that. So once you create a username, you probably have to restart your VCV rack, so it loads with your username. And then you can go to manage plugins. That takes you to the VCV rack website with all the modules. Okay, and as I said, we are looking at count modula library. There it is. And one of the devices there is the matrix mixer. So you get a whole lot of others. Bloody hell, that's proper large amount of stuff. Great. As I said, above 2,000 modules currently available. Never get there. And here's a flip-flop, for example, which is a low-level ancient computing device. Gate to trigger. Maybe I should definitely do something with flip-flops. Is that how you call slippers as well? Flip-flops? I'll just do a little reminder of stuff here, because knowing myself, I'll probably get distracted and forget about it. Well, actually, I probably should have taken a slightly more time looking at all of this, but here is the matrix mixer anyway. Gate sequencers, step sequencers, little mixer, and then there is Lunetta modula by count modula. So it seems like that's a different library. Okay, so hopefully in the meanwhile you have managed to download the count module or subscribe to, right? That's what we need to do. It looks like actually it has forgotten my login, so hell, I won't go through figuring out what the password may have been. But I have it already, so it's here. So let's look at the operation of this, okay? So it is a 4 input, 4 output mixer. It's organized in a matrix, and every output has a connection to every input. And each of these connections has an attenuator, which can also be an attenuverter. So I've briefly talked about attenuverters last time. What they do is they allow you to change the gain of the signal, but also invert it. So what I'm going to do is I'm going to grab an oscillator now. In the first 2 lectures, we've looked strictly at built-in VCV stuff. Now that we are departing from those basics, you just can see them here. I feel free to kind of explore. I didn't even hear all these different oscillators myself. Young VCO looks like an interesting one. I seem to remember bits about this. Now, in any case, what you do then is left-hand side are the inputs, right-hand side are the outputs. Oh, sorry, the bottom you have the outputs. So what I typically do is use the last output for the actual signal out, which makes it that my last column here becomes the mixer for the audio signal, because the rest will also be audio signals, but they will not be audited. We're not going to listen to those. We're going to use those for our feedback fun. Okay, so just to test this, here is my oscillator. So now I'm exploring this as we speak. Let's see, frequency modulation curve. Okay, there will be some curvature. It looks like it's pulsating right there. Okay, you can also track that this thing is kind of not black, but changes color. And then this is now on a bipolar setting, which is the attenuverter, which means that halfway setting is muted, is total attenuation. So if I turn it up for the positive direction and turn up the pot for the whole column, don't forget these are turned down by default, then I get to hear this oscillator. Now if I do this, I'm listening to inverse phase, but it doesn't make any difference in what I hear. And it will do once the things get in interesting feedback loops. Okay, so that's my VCO. So let's do a little practice here. Well, let me just do the first thing myself, and then I'll try to set up a task. If in the meanwhile, if you have experienced last week's kind of exercise setting, the kind of 5-minute exercises, you can let me know whether you found that successful or not. Okay, so what I'm going to do is I'm going to have a look at all the filters that I might have available here. I expect quite a few. There we go, diode low-pass filter. In the analog world, diode filters are crunchy and dirty and all the other good properties, I would think. So what I'm going to do then is I'm going to take the first output and send that to the filter. Okay, so I'm going to kind of arrange it at the bottom to go with this arrangement that the bottom is where things are going. And then I will take the low pass output of that and go to the B channel. Okay, so what that does, it allows me to have all the different patching available just on the dial. So I don't have to repatch, but with the dial settings, I can control the signal flow. So I can listen right here. I'll take it to unipolar so I can mute it by going all the way down with the pot. So if I slide up the A4 pot, right, so the A input to the 4 output, then I just hear the oscillator. Now, if I want to send this oscillator to this filter, what I have to do is I have to slide up. I'll take everything unipolar. I have to slide up. Well, actually, now it's slid up already because it's in the middle. The A1. Okay, so now I expect this A signal to be mapped to the first output. Let's do full on. And this first output, right, goes to the filter, and the filter comes back into the B input. So actually, I should be able to hear that filter here on B4. So if I increase the frequency there, response, saturate, hello. And we're quickly going to get into troubleshooting, it seems to me, which is a great practice, obviously. Not having a really healthy posture here. So let's see that. Troubleshooting, oscilloscope, which should be one of our best friends here. Here's the scope. Okay, and what do you do with the scope? You probe all the possible points. First thing, does this oscillator do something? This oscillator does something. Okay, does the first output here do something? It doesn't do anything. Trick question, why not? You've seen it. The question is whether you were attentive enough to figure it out. Why didn't I get a signal from the first output? Everyone's gone to sleep. Hello. Unipolar, no. A unipolar is the situation here. I can toggle between unipolar and bipolar. And actually the fact is that this is full right, full on, which would be full on in both unipolar and bipolar cases. But if you're bipolar, then this middle position is mute, full attenuation. Left is negative phase, right is positive phase. If you're in unipolar, this is half gain, right is full gain, left is zero gain. So it is not the unipolar bipolar switch. Instead, it is, there's no input to the filter because the output is muted. Yes, so that's the trick here. There is another dial here. And there we go. Thank you. So now we have the input to the filter. Okay, now we can verify, is there an output from the filter? Okay, saturate CV. You see that actually might be an issue. Am I doing everything well here? It seems like. So, you know, it's free for all. You can't count on things. And I have stuff on high pass out. I don't have stuff on low pass out. Okay, lucky I've checked both. And the probable reason there is that, well, actually I have a little bit of stuff there, if you see it. The reason here is that the frequency is really high. Okay, great, debugging on the way. So that is my currently audible filtered sound. That's my resonance. You probably don't hear this in great quality. I don't either. I rely on you patching these things as we speak. And obviously you might not have this filter. If you're interested in this one, this is a Lindenberg research library. Okay, so far so good. So this is going back into the B. So the last thing there is, that's what I'm listening to. You see, I'm listening, this is my filtered sound now, and this is unfiltered, okay? And now comes the funny thing, that suddenly I have one dial, the B1, which is the feedback dial over this filter. So you see this filter goes from channel 1 into the filter, from filter into channel B. So with this dial, I take the B channel into one output. So this is my feedback dial. So the scope has stopped answering, but I don't really hear an audible signal difference. Let's see if I can push it a bit. Okay, something is happening with this feedback control. This would be a clean signal, just straight oscillator through filter. Inducing feedback does this. Okay, in the actual analog world, this might already start to get chaotic and intermittent, but it's typically slightly more difficult to get to those exciting things in the digital counterparts, partly because you have an inherent delay. Okay, so in the analog domain, when you connect the cables, you establish an electronic circuit, which in many ways behaves as if it knows what's ahead of it. If you've ever done some basic electronics, it's one of the mind-boggling things. In terms of us modeling these behaviors, you know, as we are mammalians able to walk circles, we can't really imagine occupying the whole circle. So our way of looking at electronic circuits is problematic, essentially, the intuitive way. So these things, these electronic circuits instantly do the thing, so to speak. Obviously, you have convergent and kind of relaxation behavior and all the rest of it. But with digital systems, what we have is an inherent delay because the digital audio is computed in buffers. The reason being that it takes a lot of CPU to set up a calculation and frequently more CPU to set it up than to execute it. So if you have all these modules, all these computations ready to go, setting them up one after the other for every incoming sample is a huge CPU spike. Continuous spike, I should say. Load, I should say. Continuous spike. It's fun. So you can't do this. That's why we do it in buffers, because then one filter is set up in terms of the set of calculation it's supposed to do. You get a few hundred samples coming through it, and then done with few hundred samples, and then the next computation is set up and then executed. So the less computation setup and the larger chunks we send through these computations, the more efficient things will run. So that's why we do these buffers. And this actually means that if the signal is supposed to go through this filter, come out of the filter, and go back into the filter itself, the delay time will be equal to this buffer size. It cannot go lower than that. And in terms of the impact of this feedback, this is crucial. And even if I had an environment where I could lower the sample buffer to 1, then I would still yield a 1 sample delay, because it has to come through in order to go back again, which is 1 cycle later. And even though it's a small delay, 1 sample at 44K, what is that? Point something 1, 2 milliseconds. It is crucial. Okay, so there is no real feedback in a digital emulation. So it behaves slightly differently, but nevertheless, I have had some success in creating bonkers chaos out of this as well. Okay, so let's get on with hopefully inducing chaos here and fun intermittent sounds by adding in a folder. Okay, so a folder, what it does, it folds the signal. I believe I have a few libraries with folders, and I've played with a few. Okay, so these are the ones I have. This one, animated circuits folding depth offset, should be fun. This one seems to have more CV inputs. This one could be fun as well. Who knows? Let's take this one. Okay, so if you guys want to follow, animated circuits is the library to get. So let's just briefly examine folders before we get into sticking it into the patch. So what I'll do then is I'll take just a basic sine oscillator. So we see what's going on. Here is my VCO. Okay, I'll take scope. So my sine wave looks a bit like this. Okay. And then my folded sine wave will have a slightly different outlook. Let me just position these away. This one goes on top. That one is on the bottom already. So what I get then is, let's get this thing to talk to us, hopefully. Am I missing anything? Input depth. It's a tricky environment. You really have to test everything, because as you see, this doesn't seem to do a bloody thing, this folder. Depth offset. This should be the CV control for the 2 parameters, of which the CV input is here. And I'm sorry to say, but I don't see anything that could be my error here. So I shall declare this folder defunct. Let me see if I have an actual working folder. I believe this one gave us some joy earlier. Here is the input. Here is the output. Okay, that looks better. Move them apart slightly and explore the parameters. So first parameter, fold. 1, 2, range. Okay, so I have a mix parameter, which is the mix between the dry and the wet. So I'm going to turn that all the way up for fully wet. And then you should see what this thing does. Only thing, it's already folded. That's the symmetry, okay. Which is slightly problematic in my opinion here. Now, the way the folders work is that they're actually input dependent. So what's supposed to happen is something similar with clipping. So you're looking for a threshold level. And once you are at that threshold, things start happening, okay? And that's why I've put an attenuator here, because this thing just doesn't give you a clean signal at all. So as I come in with the sine wave, you see actually about a third way up, I get a full sine wave with a few harmonics already, which I will attend to in a bit. And then as I go beyond that threshold, I'm folding the sine back against that threshold as if there was a mirror. And then the funny thing happens, it kind of mirrors back at itself again. So now I'm taking over with this fold. So you see that actually this fold command, the parameter, I should say, is essentially a gain, right? So, and that's common for all kind of distortion, nonlinearity type processes, that the parameter, which is typically called dry, is essentially a gain before the nonlinearity, and the more you push into the nonlinearity, the more it will produce harmonics and other distortion components. Okay, so that's that. Let's look at these other parameters. So if I have a kind of a mild folding situation like this, then this range doesn't seem to do much. This is the CV for the fold. I have the 1 and 2 algorithm. Well, I can't really see a difference now, except the kind of the amplitude when it hits. Okay, and then I have this up-down folder parameter, which might actually do stuff only once I am well into it, but it still doesn't. Let me see up and down. You see, it's quite crucial. I mean, obviously, I have a fairly educated set of expectations in confronting the folder. But even then, things can be opaque. So let's go back to this basic folding situation. So the symmetry, that one does work. So you see what happens? You get the two thresholds to become asymmetrical, and therefore this behavior changes. And then the mix is the mix between the original and the folded signal. This is the CV mix. Maybe if my symmetry is skewed, then the up-down does things. The up-down doesn't seem to do things in this case. Okay, so that's my folder. So as you can expect, you know, it is a kind of a distortion. It's a nonlinear thing. So there is a linear portion where the audio is unchanged if it's sufficiently soft. And as soon as you push it beyond the level, it starts to do funny things, crazy things. So let's briefly listen to that as well. So instead of a lot instead. I'm not even listening to anything there. So here is the, keep patching it wrongly. Here's the sound of my sine wave through this folder. That's what happens there. And then the symmetry does this. The mix obviously goes back to the original sine wave. And this up and down doesn't seem to do much. And this 1 and 2, so far, it just seems to be another gain switch, really, unless I've omitted something. Now, most of these modules, unfortunately, have no user manuals or descriptions. I challenge you to find it, and please do. Maybe there is something wise in there that will tell us what the up and down is supposed to do, but we didn't get it to do stuff. Okay, so that's a folder. You've seen a few more. That's the basic principle. There are a few more potential parameters here, but essentially this kind of symmetry is crucial. And the other thing is essentially the gain into the nonlinearity. What you have is that in case of asymmetrical clipping already, the huge difference between symmetrical and asymmetrical is that symmetrical clipping will give you only odd harmonics. And asymmetrical clipping will give you also even harmonics. So if you are looking for a tube-ish sound, one characteristic of valve-based nonlinearities is that they are asymmetrical and have even harmonics as well. Transistor-based distortion electronics typically are symmetrical. So this kind of symmetry is always quite crucial. And we might actually try to verify that. So we're getting deeper into the matter. I believe I have had, let's see, some luck with some spectral display here in the past. A way of displaying the spectrum. Cube was not it. Oh God, now I'm in trouble. Because I don't seem to remember what was the name of that thingy. I mean, to go through all of this is a bit. Oh yes, Spectra was one of them. I just remember that I had two, and one of them worked nicely, and the other one was a pain. Okay, so this is my spectrogram. So I have the time passing, and I have the frequencies up and down, and then the color indicates the amplitude. So now I've increased the amplitude, so you see all the harmonics. If I take my wave folder down to become a sine wave, and I switch to the digital sine wave here because the analog is just making harmonics on top. Let's get this in a totally linear zone, hopefully. And let's get our symmetry straight. Okay, there was 1 point there. Okay, so what you see here, I'm in a very kind of a gentle area, almost linear, but not quite. I have one harmonic on top. But you see if and that's when the symmetry is bang in the middle right now. And as soon as I move the symmetry away, that the second harmonic there starts to appear. Again, if the symmetry is straight up, which means symmetrical, then I can remove the second harmonic. And then if I induce asymmetrical transfers, then I get the second harmonic. Obviously, I can increase the fold here to get multiple harmonics. Let's get this back down so we see multiple of them. So in this situation as well, if I hit bang in the middle, I might find a spot where the even harmonics disappear, and then I bang it up again, and then the even and odd harmonics are both there. Okay, good. So that's the operation of the wave folder. Maybe I'll keep the spectral analyzer there, although I hope that the sounds will speak for themselves. So what I'm going to do now is I'm going to take this wave folder and stick it into the matrix mixer in the similar fashion. So I'll take the second channel for the input. The output will then go back into the C channel. So now this becomes my second. Well, actually, this becomes, what am I saying? So C2 is my second feedback path, right? So things are getting progressively more complex here. I mean, if I take all these down, let's kind of shut everything up just to make sure we get what's going on, because it's getting increasingly complex. Yeehaw. So I'll take all of those down, take all of these up, because they tend to confuse me, because I forget about them. My actual matrix mixer in my rack does not have these, so in all honesty, just a second ago I forgot about it. So all of those, everything is unipolar. Let's do a mixer reset. All the engineers love a mixer reset when someone else does it for them. Okay, mixer is fully reset. Everything is on 0. Okay, so first channel, A4. This should be my clean sound. Okay, so let's listen to that. There it is. That's my clean sound. Okay, so I can send this clean sound to the filter like that. And then, well, I'm monitoring something, so I'm just going to remove this to avoid confusion. So now I've sent the oscillator to the filter. The filter goes back to B, so I can hear filtered oscillator here. Okay. Now I can also send the oscillator to the folder with this dial, and then the folder feeds back into C, which is this one. So this is my folded sine wave. Okay, so we've heard that if I send my oscillator to the filter and I listen to the filter, I can induce feedback, intermittency. I mean, I don't know how well you hear this, but it goes like, there is a kind of a rhythmical aspect to the sound which is unaccounted for in the sense that there is just an oscillator and a filter. So you're not supposed to get intermittent stuff unless you feed them back, which is what we're doing. Okay. And now what I can do is I have two options, right? So I can send the oscillator to the folder, comes back again, and feedback that. But I can also do a different type of cycle whereby I go A, B, C, and back to A. I can go A to B and back to A to C back to A to B to C back to A to C to B back to A. So all the possible combinations in terms of a single feedback loop, in terms of over a signal module, and a feedback loop over two modules in both variations, all of this is possible without patching, right? All of these combinations are available through these dials. And that's the power of matrix mixing in inducing feedback. And even more powerful is the fact that you don't really have to figure it out, because once it's starting to make the kind of noise you want to, you can just play away with the dials. Okay, so let's see if I can get some more horrid intermittency here. So this is a single feedback loop around the filter. So what I'm going to do is I'm going to send that from the filter into the folder. Okay, and from the folder, let's first just listen to it. Okay, now I want from the folder to feed back, and I have 2 points where I can feed back into. I can feed back into the filter or into the folder with these two. So this is feeding back into the folder, rocking it, kind of like it here. And this is the feeding back into the filter. And this is where you get what we call sensitivity to initial parameters. You get this, very small movement there, and the sound character jumps completely. And if you manage to set your parameter just where it does the change, that's where you get the most intermittency, the most chaos, which is just here somewhere. Let's see if I can do this very finely. Okay, there it is. So you get this rhythmical pulsation, which sounds random, it's intermittency. Okay? And I could just play with the parameters. So you see it's funny, here it sounds continuous. And there are these few bits and it goes crazy. Nice. I have a kind of a behavior, so it jumps harmonic. Okay, and I can have a bit more fun. Let's do another feedback loop here into the curvature parameter, which might have a, yeah. Didn't quite explore these ABCs, to be honest. Straight into the frequency. More feedback. Okay, obviously I could have fun with this for a while. And it's a fairly basic, I removed this feedback, it didn't do too much more on top of what we looked at. So that is your basic recipe for chaos. You get into a folder, you get into a filter, and you just do a whole lot of feedback. One thing that might be interesting is what happens if I remove the oscillator. It still does chaotic stuff. And that is your basis for essentially no input mixer genre. Look it up if you haven't heard of it. You can actually have a proper matrix mixer. I actually have an 8x8 old Adam Audio thingy. Huge thing, the size of a double bed almost. Maybe a child's bed or something more modest. And you know, it can just provide endless amount of material without any sound source, just feeding it back into itself. So that's your matrix mixer and your folding. Okay, so I hope that was fun. Let's see, are there any comments? Martin says, wow, sorry, Marin, wow, back at you. So let's try to conceive this patch on a flowchart, because that will help our understanding, and it will allow me to a little task for you lads, because that's crucial. Okay, so what I normally do here, you've seen me do this, I'll have something that I call a matrix. This will be my, well, let's just give it a full name, matrix mixer. It's going to be my biggest blob anyway. I shouldn't have lost this side bar here. Okay, so let's make this nice and neat. I have a stroke, a lovely box around this thing. Okay, so this is my main thing, and then evidently I have an audio output which goes out from the matrix mixer. I typically use the 4th channel because it kind of isolates. You've seen this happen. It kind of allows you to conceive of the main difference here, because these are not feedback pots. All of these, well, most of these will become feedback pots. In fact, what you're looking at is that the diagonal here, below the diagonal, you get feedback pots, right? Because if this is my source of sound, then this is not a feedback pot, it's just oscillator to the filter. This is the oscillator to the folder. This is the oscillator to a third potential process, right? So as they come, these are still just plain pots. But this one already, because it's coming back from the filter and going out to the filter, is the feedback pot. So this diagonal, if I maintain this patching principle, this diagonal becomes the set of feedback pots around a single process, and everything below this diagonal will be a pot around 2 processes. So this would be my pot, which goes feedback from after the folder into the beginning of the filter. So it encapsulates 2 processes. It's a double process feedback. And this one, if I've patched the 3rd process along the same lines, will be the one pot that controls the final loop around all 3 things in series. Okay. Cool. So what we are looking at here then is a situation whereby, I don't remember which one was the arrow. This one is my arrow. Okay. Nice and neat. Let's get an arrowhead on there as well. Cool. So matrix mixer goes to the out. I typically use the 4th column for that. We had a few processes. Well, first thing we had is a VCO in the left channel. Okay. And then all these other processes lining up, which will be used in a feedback fashion. So in setting a task, what I'll do is I'll have a low pass filter and a folder. That's my current setup. And then what I'll add to this will be a high pass filter. And these essentially each have their own channel for the output, which was channels 1, 2, and the future 1, 3. Okay, and then each one of these are actually going back to the matrix mixer, which is gonna make my little graph look stupid, because that's what I need to do, right? Now I would love to kind of go a long way around there. So what I can do is I can maybe make this slightly more complex, but slightly easier to read if I actually do a channel block. Take this one. If you remember, inputs were labeled with letters and output with numbers, such that you can get things like A1, A2, A3, and so on. So I will actually take separate labels there for the 4 input channels, just so I have it slightly more transparent. And then what I can also attempt to do is make this kind of readable by saying, okay, here is that feedback loop. I'm not sure how. Well, in any case, the VCO goes to the A channel. Okay, I will stick these here on top. In fact, maybe the best thing is if they become part of the blob. Something like this. Okay, so these are part of the matrix mixer. And then this LPF signal goes to the B. So let's see if I can get this done nice and neat. So that is my B input. Remove those arrowheads. Be slightly pedantic. I guess you guys in the meanwhile are making a huge amount of noise with what you've got. At least that's what I'm there to hope. So here's my second and my third feedback loop. I'm not sure how much effort I should make at this stage to make it all nice and neat. You see, it's not trivial, but this would be the C input and this would be the D input. And hopefully, no, these things didn't quite attach like that. That's just one way, not the other. But we have to get them to connect again. Okay, am I safe now to move it? Blah, blah, blah. No, these points don't move together. Don't move together. Okay, well, you see me failing in making this a very nice and readable thing. No, these points don't want to move together. But hopefully you can follow it a bit. What if I do this? Yeah, maybe that's kind of easier to appreciate. Yay, I like that. Okay, so that's our setup. Obviously, what I could do as well to make this even more clear is make a 1, 2, 3, 4 output here, which is actually worth doing because it's not the thing that is very easy to immediately understand. Especially when you start patching different things in there and things get complex. But if you get there once, in terms of intuitively understanding your matrix mixer, then you stay there forever. It's like riding a bicycle. You don't really forget a matrix mixer once you've met it. Oh. Okay, so maybe that's even neater now in terms of actually labeling how the channels are connected. Okay, so a little break. I'm gonna make another bevy here. And I invite you guys to stick in the third or the second filter, find something in there, and then get some seriously interesting sounds going, please. And then we'll be back. So let's take a generous break just to give you time to play with this and try to fix this arrangement. So let's be back at 8 o'clock on the dot. And then depending if you have some interesting questions, want to show us, share the screen, share the sound, I'll be very happy to discuss these things. Obviously, if you find something not working and similar. And otherwise, we'll get to the other basic analog processing strategies. So I'll see you guys in 15 minutes or so. Good. I'm gonna keep the image on the screen, maybe you need it. And hello everyone, we're back. Good libraries. Jago is off. All right. Hello. Goodbye. Yeah, good libraries to subscribe to. There's just too many. There's just too many. You'd have to, but that's also quite cool, really, because you can, you know, you get to select your weapons. I think up to 10 is maybe worthwhile subscribing to before you get overwhelmed. And you probably need a month or two with 10 libraries, I would think, to really go through most of the modules, see whether it's worth or not. Supposedly from VCV Rec 2 on, we will have the ability to load a single module, not the whole library, as a chunk, which will largely help maintain an oversight, a kind of a manageable library of your own. But yeah, I mean, just roll your own, man. Get your I don't know if I can come up with further silly slang here. But just keep trying them. Okay, so does anyone want to share the screen and audio and show us how something crazy happened with the feedback loop, something awful, something something crucial, interesting? If still patching, okay, well, you can keep patching forever anyhow. What I'll do then is go through a few more things in the last half hour that should probably be quite interesting as well. Okay, Tom, let's go for it. If I stop sharing, then you should be able to share yours. Let's see what you've got.
I have a kind of crazy patch, and I can't really hear myself at the moment because it's kind of loud. I don't know how I share my like desktop audio. Can I do that?
So you have 4 icons. You have the message icon, then you have the people icon, and then the third one is the share content. You click on that.
Yeah.
And then there should be a share screen application, and there you can pick your desktop screen.
Okay, can you hear this?
We can see it, we can't hear it though.
Okay. Let me see if I can
Looks funky.
It is pretty funky. I don't know how to share my like audio. But like I put this delay module in, and like depending on how I vary this parameter, it kind of goes between being like really crazy and noisy and kind of like chill. So it sounds cool. I wish I could like share the audio here, but I can't seem to. How do I stop sharing? Oh, there we go. Okay.
All right, so nonchalantly, I have just closed the window, sent you all to hell and back. But I see Tom is not sharing stuff anymore, so you found a way, it seems. Okay. So yeah, I mean, hell, looks like you've done something. Looks like it makes a nice noise. We'll find out maybe once you make a track. Great stuff. Okay, so yeah, as I said, as I started saying before, I probably closed everyone down. One of the ways to do the sharing the audio would be through Soundflower. So it's a kind of a small app. You install it. It appears as a separate audio device. And then here in Blackboard, what you can do is settings, and then audio, video. There I went again, back again. So in the settings, you can set the input to be Soundflower, and then the VCV rec outputs to Soundflower, and then it goes straight between the apps. That would be one of the ways. But obviously, let's not take too much time with that. But instead, discuss some other low-level modular type processes. Okay. Right, so I'm going to remove this. You can patch it any day anyway. Maybe even the matrix mixer, although it might be interesting to see whether any of these processes get chaotic, potentially. Cool, so one thing that we've stumbled across was a flip-flop, which is kind of a component of digital computing. But I guess you might understand that digital computers are analog, because there is no such thing as a truly analog signal. The fact that a signal is called digital has everything to do with how we approach it, how we look at it, because the voltages just don't come in a stepwise fashion, in a binary fashion. There will always be noises and stuff. They're actual signals in the computer. It's just that the significance of the signal is different, and you consider it a digital signal. So all you're interested in is below or above a threshold, on or off, and a bunch of those at really high gigahertz rates give us digital computing. So an algorithm is digital, but an electronic component is necessarily analog. An A to D converter is analog component. D to A converter is an analog component, which is a funny kind of perspective. Okay, so flip-flops. What do we have here? We have a modula, count modula. This is also count modula. All of these are count modulas. We have a trigger flip-flop. We have a set reset flip-flop. Okay. We have a dual trigger flip-flop, and we have a dual SR flip-flop. Okay, let's get a set reset flip-flop. Let me think. This one has two inputs. Let's get the basic flip-flop first. Okay, so what does it do? It flips and it flops. Ha, you've guessed that one. Horrible jokes for today. It can't get worse than that. Let's get an LFO. And let's get an LFO which actually gives us a square wave to examine what the hell a flip-flop is doing. So typically what I expect it to do is, on one trigger it goes positive, on another trigger it goes negative. Okay, so a square wave, an LFO square wave, fairly slow should be, let's try to get that to display. Here we go. That's my square wave. If I send the square wave into the trigger input of the flip-flop, the other Q input looks like this, which is slightly worrying, but it could, there we go. That's what it does. Okay, so what happens is on the first trigger, it flips up. On the second trigger, it flips down. Done with. Okay, so that's the charm of it, right? We are looking at very simple building components that make up the world around us. So I kind of hinted at this in the first class, but worth repeating. So what is a trigger? Trigger is a way of looking at a signal, right? So all the signals in VCV rack, in an actual analog rack, are interchangeable. There is no distinction. All of those are just voltages. The idea of signal being a trigger has to do with observing it. In fact, observing the moment when it goes from negative to positive. So that jump over the 0 line is the moment of the trigger. So it could be any signal. It can have any amount of detail. It could be a square wave. It could be a sine wave. If you are observing it as a trigger, you will be observing the moments when it crosses the 0 line, and only in the upward direction. The downward direction crossing doesn't count. Okay, so this means that any signal can be considered a trigger signal. I can input my voice in here as well. In fact, it might be coming out of this thing already. Let's see, does that work? Just scope the first output there. Hello, hello, hello. No, it doesn't seem to. Apple built-in audio device. Blah, blah, blah. It doesn't seem to. Core audio. Because this is the built. Okay, I might have to take another audio, which is a bit funny, but let's give it a try. It could be fun to process my voice as well. So how about this one? If I select built-in microphone, allow it. Okay, there it is. Oh, there's my voice coming out. So this could also be a trigger signal. So this is what happens. So what does actually happen to the frequency of the square wave as it goes through a flip-flop? A question worth $1 million. And the answer is, I'm looking at the chat. Switch on your microphone if you want to be fast and win the lottery. Everyone, is anyone still out there? Anybody out there? What happens to the frequency? If you just give me a no clue or some response there, because otherwise I'll consider everyone to have fallen asleep. Or okay, hello Marin. So the question is, what happens to the frequency of the square wave as it goes through this flip-flop? The frequency is halved. Excellent. So this is what we call a subharmonic distortion, right? So every process that induces new spectral components is typically a non-linear distortion process. And basic things like clipping, like folding that we've looked at, they create harmonics on top of incoming spectral components. In fact, on top of each one of them. And they also create intermodulation components, which are sums and differences of all the incoming spectral components, just to make things even more dense. And finally, in an environment which is digital, aliasing is also likely to happen. And now what we've just looked at is a process which creates a subharmonic component, a component which is lower than the incoming spectral component. In this case, the second subharmonic. Okay, so we can probably listen to that. I mean, it won't be horribly exciting. You'll just hear a square wave of half the frequency. But what might be potentially more exciting is if I now take the voice of Neon, and there you see square waves happening as I speak. And let's give that a listen, I would say. So here we go from the folder. I'm probably going to have to speak a bit louder. Hello. So matter of warning, don't wear earplugs, guys, when you do this. You know, this could have been fatal for speakers, ears, all the rest. Be careful. So what happened there is a huge amount of feedback, so I should be more sensible than that and take it through an attenuator just to ease it in. Hello, hello. So there is the voice doing stuff, and if I keep talking, maybe I will start to hear something happening. Hello. is this. Oh, I didn't connect something. So this is the thing. Oh, let me just drop the volume before I do the same thing again. So here we are slowly introducing it. So it's a subharmonic thing. So if I sing, oh, well, you didn't quite hear the subharmonic there. Hello. So actually what I'm doing now with my hands, you don't see this, but by covering the speakers and the microphone physically with my hands, I control the amount of feedback, right? Because now the feedback goes through the microphone and the speakers, but there is a serious non-linearity in the middle, which means stuff is funky. So now I've laid my hands to cover it. I can kind of make it shut up, just like that. Okay, and now I can slowly open my hands. Hello. Okay, enough said. So again, a non-linearity in a feedback loop. This time, not a digital feedback loop, but an actual speaker microphone feedback loop equals fun. Cool. So that's the flip-flop. Okay, so the more frequent set of processes that you will find, which are very similar, are dividers. And a divider typically does what you've just seen, but you will get different counters inside. Okay. So what actually happens with your flip-flop is, I mean, in the circuit, it is actually a fairly simple transistor-based thing, if I have it right. That has this property of kind of switching a signal on and off based on an incoming signal. But actually, what you have in analog domain very often are counters. Although in Eurorack, by the way, it seems there is no real counter. So a counter will be a device that would make a stepwise climbing every time you get a trigger, and typically they have the count maximum such that once it goes up sufficiently, it just drops down. So it kind of gives you 1, 2, 3, 4 type of counting behavior. And then typically if you connect a counter like that to a kind of a gate, which is waiting for a trigger to start the gate and for another one to close it, something like a flip-flop, which you've seen, then you can get further subharmonics, right? And that's a clock divider. So what I'm looking at here, I'm not sure, do you see guys, if I zoom in like this, I'm not sure if you see that, plus won't work, but I have a few here. So I have this leftmost aridacity clock divider, which has clock reset and inputs, and it has 16 outputs, so all the integer outputs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I have the Omer modules RKD rotate clock divider, where I can set the actual divisions as well. Similar thing, multiple outputs there. Then I have the count modular voltage controlled frequency divider. So let's take that one. So what it will do then, on top of what we had so far, is it will allow me to have further divisions. So for some reason I've lost my LFO, so I'll just retrieve that. Little Mr. LFO, here we go. Square wave to the input. Let's look at it as well. Let's get a viable frequency here. Trigger, slow trigger. Hello. Is that too slow? Okay, so I'm seeing a square wave. That's my objective. Cool, and then I have a bipolar out and a unipolar out. So bipolar out will go negative maximum, positive maximum jumps. Unipolar will go 0 to positive maximum jumps. Let's do a bipolar output. Here it is. And currently what you see is that I'm getting the exact same square wave. The position is a bit skewed. There we go. Okay, and then I have a manual control of the amount of subdivisions. Here's my division by 2, division by 3, division by 4, and so on. And I also have a CV that will do this. Okay, so a CV input, meaning that I can send in a signal that will change these behaviors. So I can try to create a stupid feedback patch, which is the purpose of me sticking around planet Earth, probably. So what I'll do then is I'll take this output, okay, and I will control the frequency of this oscillator with it. And then with this oscillator, I'll play it quite low, and I will take the triangle wave and control the subdivision. Okay. And then if I play with this, well, what I expect to happen is, first of all, get a stable number of kind of subdivisions. So I can start listening to the signal to figure out whether it makes anything intermittent. And it seems like it does already. So it does this acceleration, right? Because I'm using a sawtooth wave to control this division. So it's not horribly funky yet. What if I plug the sawtooth wave back into this frequency? Nothing horribly exciting there. Okay, evidently I could have more fun with this. But what you see now is actually I've created some feedback loops trying to find unexpected sounds, as I do. But note that in this situation, I didn't plug the audio back into an audio input, but I've actually plugged back into frequency CV input. Okay, so it's a slightly different thing. It will have different results, but I guess that's the message. You know, kind of get to exploring these things. Okay, so we've looked at dividers, we've looked at flip-flops. Let's look briefly at sample and hold, which is another kind of analog typical thing. Sample and hold, this one will work as sample and hold. Okay, so what is sample and hold? Well, what it does, it takes one input and it takes a trigger input. And every time a trigger arrives, it will sample the actual input, right? and stick to that value until the next trigger comes. So it's actually quite akin to an A to D converter, in that it creates a stepwise function. However, you could have an odd sampling period. It doesn't have to be steady, and it might serve totally different purposes. It might serve to kill speakers and members of the audience. So this random is a useful built-in module there, because it actually gives you a stepped random signal anyway. So that's what's happening now. So at a fixed interval in time, every so often, I will get a fixed voltage coming out of a different level in a random fashion. And this now acts as the frequency control in terms how frequently will I pick a value and stick to it, right? So you see, I can actually have it fairly infrequently. Every now and then, this value will change. I can also have it kind of stepwise thing. And the step output is the one that does that. So I'll plug in that into my sine wave. So you can briefly hear how that pans out. Okay, so I get this kind of R2D2 thing. Can I call it that? Okay, bipolar as well. Okay, so that would be one way of using it kind of on its own. So it has an internal noise generator, it has an internal trigger, and it sample and holds that noise on its own already. But what I can also do is I can take an external input, and in this case I will take a sine wave just to make a contrast there. And if I increase the trigger speed here, what we're supposed to get, let's increase the speed of the sine wave as well, okay, is our quantized sine wave. You see, so every now and then I'm taking a sample of this sine wave, sticking to that value for a good time. I will, this actually looks okay, okay. So that's my sample and hold sine wave. And this is now having a sample and hold happening at fixed intervals. So the last thing I can do here to make it even funkier, you can also listen to this, although it's an LFO. I don't have a sub here. So the last thing to think of is how could I make the sampling interval random? And in order to do that, well, I actually need a noise source or just another random, right? So now I know that if I increase the rate here, it's almost as if I'm not sample and holding it. So actually the output of that, and let's verify it, now should be pretty much noise. That's what we have. And now I can use this noise as a trigger signal, which means that the crossings here will occur at weird intervals. So if I use this for the trigger here, then you see my sampling the sine wave has become noisier. Okay. So this is actually sample and hold, whereby I have a randomized trigger, but my actual signal is a sine wave. So what I expect then to hear is a kind of a fixed frequency coming through a little bit, at least. So what am I doing here? This is my output now. Okay, so let's listen to that. Okay, so you kind of hear the noise coming out of there. And you get a sense of, wait a minute, I think I removed connection. So this sine wave, external in, no, it's actually fine. Yeah, because I have a noise, I'm not using this sine wave. Okay, So I can actually hear this frequency coming through. And at this stage, it's almost like there's an extra source on top. But if I play with these values, I can get these types of behaviors. Okay, and then you might have expected that I'm going to try to induce a feedback loop. So how about I take the linear interpolation there into FM1. Okay, so you can have fun with that. That's your basic sample and hold application there. Now, the funny thing here is that it's a bit more difficult to assess whether I actually got to a chaotic thing due to my feedback loop, because there is a random signal in there already. So I cannot rely on my sense of intermittency. But what I can rely on in terms of detecting chaos is the situation that you've seen, whereby in the life of a dial, right, there are bits where the difference is huge, and then, you know, huge ranges where there's hardly any audible difference. So that's another way to detect actual chaos. Not trying to say that, you know, if it's a chaotic thing, it sounds good and otherwise chuck it. It's just about, you know, getting cool sounds out of this thing. Cool. So time's gently up. Unless there are any questions, I'm tempted to call it a day, and hope to see some of you next week as well. Not sure what I'm gonna think of next week. Probably go further into the kind of analog specific processes, low-level stuff, debugging using the oscilloscope, kind of establishing the foundation which will allow you to explore on your own. So thanks for being here, guys. That's my goodbye hand, and I'll catch you next week.